Hi guys, welcome to another video. In this one we're going to be going through the paper 1, that's topics 1 to 5, and the paper that I've chosen is a 2021 paper. Now the first question is on the periodic table and it says figure 1 shows part of Mendeleev's version of the periodic table. Which group of elements had not been discovered when Mendeleev's version of the periodic table was published? Now the best thing to do is look at the periodic table you got in front of you, look at the one that you'll have in the exam, which will be on a data sheet, and then quickly scan it to see which elements are not present in the one that you have on the data sheet. So if you look at that one, you'll see that no group 0 elements are present, no noble gases. So it would be group 0 that are not present. Moving on to the next one. It says figure 2 represents different models of the atom and it shows you 4 different types, A through to D. Which model represents the plum pudding model? Now I know that that one is B. The reason for that is because I know the definition of the plum pudding, which is a positive centre with negative charges scattered around it. And that's what you've got here. You've got a big positive centre, or a ball of positive charge, and then you've got negative electrons scattered around it. Okay. Which model resulted from Chadwick's experimental work? Now I know that Chadwick discovered the neutron. I'm just going to note that here. So Chadwick discovered the neutron. So which one of these has a neutron in it? Well, B doesn't. I can't see any neutral charges. C has nothing in it. It's just a spherical shape there. And then you've got this one here, which is the nuclear model, but I can't see any neutrons. It just has a 4+ in the centre. It's actually A because it shows you the neutrons here. Subatomic particles with no charge. So you can see the 5 neutrons there. So it must be A for that one. The next one says potassium has different isotopes. What is an isotope, or what's meant by an isotope? You should refer to subatomic particles in your answer. Right, so it's telling us that we need to talk about the particles in an atom in our answer. So that's what we're going to do. An isotope is where you have the same number of positive protons, but a different number of neutrons in the nucleus. And that's that one. The next one shows table 1 and it says it shows the mass numbers and the percentage abundance of 2 isotopes of potassium. Now abundance means amount. So the amount in percentage of the 2 isotopes of potassium, calculate the relative atomic mass, so the AR of potassium, give your answer to 1 decimal place. Okay, so looking at what we have here then, we've got the mass numbers on the left and we've got the percentage abundance on the right. In order to work out its AR, we have to first do the mass of each isotope multiplied by its abundance and add it to the other isotope. So the mass number of the first one is 39 and its abundance is 93.1. So 39 multiplied by 93.1, close brackets, and we're going to add it to the second isotope. So the mass is 41 and its abundance is 6.9, and then we divide by 100. It will always be 100 because you're never going to get more than 100%. And I'll do this on the calculator very quickly, and we get 39.138, but we only want 1 decimal place. So the answer is going to be 39.1. And there you have it. Moving on, we've got number 2. So the second question says acids react to produce salts. Universal indicator is added to water and then nitric acid is added to the mixture. Give the colour change when nitric acid is added to the mixture of universal indicator and water. So we have to think what's going to be the colour of the water before the acid's added. Well, you should know that water is neutral and therefore it will give a colour of green when universal indicator is added. So it has to be one of these. Then we add an acid, and acids have the colour red in the presence of universal indicator. So it would be green to red. It's alkalis that give the purple colour, so we know it's not that one. Okay. Number 2.2 and 2.3 for now. So we've got what happens to the pH of water when nitric acid is added. So if you think of the pH scale, we have 1 to 14. Right at the very top, we have your alkalis. And right at the very bottom, we have your acids. And then in the middle here, you have your neutral water. Now we know that water is pH 7 and it will be green with universal indicator. And when we add our acid, it's going to move down. The pH will decrease. And what is the state symbol for nitric acid? Now this is important. It says the symbol, not what state it's in, what state symbol will it have. So it's going to be in solution. Use AQ for a solution, aqueous. Now the only liquid, because the temptation is to write liquid, the only liquid you will know is water. That's the only one you'll have to remember in chemistry. Water is liquid. So if I ever ask you a question like this and it's not obvious that it's a solid or a gas and you're trying to think, well, is it a liquid or a solution? It's most likely to be a solution unless you're dealing with water. Question 2.4. It says zinc carbonate reacts with nitric acid and the word equation for the reaction is, and it gives it you there, give 2 observations that would be made when zinc carbonate is added to nitric acid until zinc carbonate is in excess. Right, so let's have a look at the equation here. So we start off with a white solid, and when we add the nitric acid, what we get is zinc nitrate, which is a colourless solution, water and carbon dioxide. And straight away, if you ever see a gas, you're going to know that bubbles will be produced or fizzing during that reaction. So I'm going to write gas given off. Now the second observation that I would see is that this white solid that we start with has gone. We get a colourless solution. So I would see that white solid start to dissolve. It says a formula of zinc ion is Zn2+. The formula of the nitrate ion is NO3-. What is the formula of zinc nitrate? Now you need to look at the charges. So we have a 2+ and a 1-. And you know that in a neutral compound, the charges have to cancel out. So I need 2 positives and 2 negatives. So the only formula that will work is 1 Zn or 1 zinc ion and 2 nitrate ions. So this one here, because that will balance out. That will be 2 positive and those will be 2 negative in total. Right, this one says acids react with insoluble metal oxides to produce salts. Plan a method to produce a pure dry sample of the soluble salt copper chloride from an acid and a metal oxide. Right, we need to first think what acid and what metal oxide are we going to use. Now we want to make copper chloride, so we need a source of copper and a source of chloride. Where are we going to get them from? Well, our metal oxide that we will use will be our copper oxide. And to make a salt, we are going to need an acid. And it says that here. What acid would produce a chloride salt? Now there's only one, and that's hydrochloric acid. Now, for those of you who perhaps didn't know that, I'm just going to quickly note down here the types of acids and the salt that they make. So you've got sulfuric, and that will make sulfate salts. You've got nitric acid, and that will make nitrate salts. And you've of course got hydrochloric acid, and that makes chloride salts. So if you remember those 3 on a flashcard, that will help you when you come to making salts from an acid and a metal oxide. So we've got hydrochloric acid and copper oxide. We need to react them together. Now there's a couple of extra steps we need to do. First, and I'm going to do these in stages. First, we need warm hydrochloric acid. And that's added to copper oxide. Well, technically, it's added the other way around. We add the copper oxide to the hydrochloric acid, but in terms of you getting the marks, that isn't going to make a blind bit of difference. You have to combine the two, and the acid has to be warm. Now, the next step is you want to add copper oxide in excess. The reason for that is twofold. One, you want to make sure you got enough copper oxide to fully react with the acid, and two, it's kind of a nice safety measure. You don't want any leftover acid. So if we can use up all the acid, then we know when we come to filter it later on that one of those issues has been taken care of. We don't have the acid. So warm hydrochloric acid to copper oxide. Should say here acid added to copper oxide, add an excess of copper oxide and stir to make sure it all reacts, and then we'll have an excess left over. So we'll basically have in our, let's say, conical flask, we'll have our solution, then we'll have a remaining solid here of unreacted copper oxide. So we need to filter that out. So filter off our copper oxide, and then finally, once we've filtered it, we'll now have a solution with our lovely copper oxide in it. But that's not dry, is it? Remember, we want a dry salt. So we have to remove the water. To do that, we do something called evaporation. And we're going to put that into an evaporating basin. And we're going to heat it, but not to complete dryness. We're only going to heat it so there's a little bit remaining. And heat until almost dry. Then what we're going to do is we're just going to leave it to crystallize. And the reason for that is, if we heat it too much, the copper sulfate that we just made might start to decompose and break down. We don't want that. So we only heat it or evaporate it until a little bit of the solution is remaining. Then we just let it recrystallize near a window or near somewhere sunny or warm, something like that. And that's it. We've actually done 5 points there for 6 marks, but there's lots of other marks hidden amongst that. So things like the warm hydrochloric acid and adding excess copper oxide, stirring it, things like that, they're all extra marks from the mark scheme. Right, hopefully you can see that 6 marks aren't too tricky, and you could possibly do that if you remember the practical. That's the key thing. You have to go over your practicals in your revision. Question 3 says, this question is about energy change. A student investigated the temperature change when 10 grams of ammonium nitrate was added to 100 centimeters cubed of water. This is the method used. Measure the temperature of 100 centimeters cubed of water, add 10 grams of ammonium nitrate, stir once, measure the temperature of the solution every minute for 7 minutes. We've got a lovely diagram there of what we're doing, and it says, what is the dependent variable for this investigation? Right, well, for my variables, I remember this mnemonic. I remember don't mess in class. Don't mess in class. And each letter, well, tells me the variable. D for dependent is something we measure, and the independent is something we change. So we want the dependent, so we're thinking, what are we measuring in this experiment? Now, we've got a thermometer here, and that's what we're going to be using to measure our temperature change. We measure it at the start and then at the end. Three improvements we could make to make our results more accurate. Well, a glass beaker is pretty rubbish in terms of insulating. So we could change this for a polystyrene beaker, or we could insulate it ourselves. So I would say use a polystyrene cup or beaker instead of a glass beaker. Now the next thing, and the biggest, is we've got a massive open top here, which will be letting a lot of that heat energy out. So the best thing to do is to add a lid. And if we're going to use a polystyrene cup and add a lid, it's going to make it very difficult to read this temperature without having to take the lid off to read it, to put it back on again. So not only would a digital thermometer be better in that respect, it'd also be more accurate in terms of the reading. So the next and final one would be use a digital thermometer. Now there are other answers available. I'm going to put the mark scheme in the comments below, and the same goes for all these questions. There are other answers you could give, but I'm giving the ones that I would do if I was in this assessment. So we've got a graph here and it says figure 4 shows the results. Explain them. Now it's 4 marks, that's a lot. So just saying that the temperature goes down and then goes back up again, that's not going to get you very many marks. We need to explain what happens and why. So I always like to use data in graphs. Whether or not it asks for it, I always think it helps. So what's happening is that the temperature decreases between 0 and 1.5 minutes, okay? So it decreases between 0 and 1.5 minutes. The temperature decreases between 0 and 1.5 minutes. And the reason for that is because you're dissolving all of that ammonium nitrate, okay? And that process is endothermic. Then finally you see an increase in temperature, a gradual increase between 1.5 and 7 minutes. And that's because energy from the surroundings is being taken in. It's exothermic. Okay, so for the poor writing there. 3.4 asks us to draw a reaction profile for an exothermic reaction, and we should label the products and reactants, we should label the activation energy and overall energy change. Okay, so we always start off with energy in the middle. Whether you're doing an exothermic or an endo, I like to start somewhere in the middle. Now you have to think what's happening in an exothermic reaction, and I like to think of this as a bank. So if money exits your bank, and this is your starting balance, what happens to it? Well, if money exits, your balance goes down. So we need to draw another line lower than our original. If it was endothermic, what happens when money enters your bank balance increases. So we would draw a line higher. So that's how I like to think of it. And then I join these two lines up with a hill, and I come back down to the start. Now, the starting line here is our reactants, and our end line is our products. So we've got reactants done, we've done our products, we now need activation energy and energy change. So our activation energy is always from the bottom of the hill to the top of the hill. Now make sure when you're drawing these arrows that it goes from the bottom straight to the top. Don't stop short, always go straight to the top. So that is our activation energy. Energy change is the difference in energy. So what you started with versus what you finish with. So it's from the start line to the end line. Okay, and that's it for 4 marks. That's a really nice question. 4 says carbon can exist in a number of different structures. The first fullerene to be discovered was Buckminster fullerene. What is the formula of Buckminster fullerene? This is just a memory task, unfortunately. You either know it or you don't. It's C60. Again, if you don't know it, flashcard. If you did, well done. You've committed to memory, nothing left to learn. Graphite is a form of carbon. Explain why graphite conducts electricity. Okay, if we're talking about metal or graphite, we're talking about delocalized electrons. If you're talking about ionic compounds, then we're talking about ions conducting electricity. So we've got graphite. So the answer is going to be it has delocalized electrons. And those delocalized electrons are free to carry a charge. 1. Steel is an alloy of iron and carbon. Explain why steel is harder than iron. Well, alloys are harder than the metals because they have different sized atoms in them. So we have carbon here, which is a different size to iron, and when they're mixed together, it disrupts the rows, it disrupts the layers. Steel contains different sized atoms which disrupt the rows. And that stops them from sliding. So when a force is applied, they don't slide, so they're much harder. So the marks here are for the different size, the disruption of the rows, and the fact that the layers cannot slide. We get onto our first calculation now. I don't think we've done many in this paper, and it says iron is alloyed with carbon and other metals to make stainless steel. A stainless steel fork contains 71.92% iron. Table 2 shows the mass of each element in the fork. Calculate the mass of iron in the fork. Right, this is quite a tricky question, and it's quite a lot of marks as well for 4. So this is what I would do. I need to know the percentage mass of all of this. Okay, if I know the percentage mass of this, I can work out how much mass is just for these impurities, and then I can look at the mass of the whole fork, and then I can find out how much of that mass is attributed to iron. Okay, so this is how I do it. First of all, let's find percentage mass. So let's add all these up. So 0.05 plus 10.44 plus 5.80. That gives us, for this one in mass, 16.29. Okay, that's how much I have of just these here. And I know that 100% out of the 100%, 71.92% is iron. So how much is just carbon, chromium and nickel? So I'm going to do 100 minus 71.92, and that means that I have 28.08%, which is carbon, chromium and nickel. Now to find the percent or the mass of everything, I'm going to take my mass, the total, and I'm going to multiply it by 100. I get 58.01 grams, and that's the whole fork. Using the mass of my impurities, what I know about is percentage, and knowing that all of it will be 100%. So 58.01 grams, but I don't want the mass of the fork. I want to know what this is here. I want to know what 71.92% of it is. So we need to work that out now. So mass of iron. So I'm going to take what I know is, I know that I've got 71.92% of it. I know that 100% of it must include my iron. So I'm going to do 71.92% divided by the total, which is 100%, multiplied by 58.01, which is my mass of my fork. So mass of iron is 41.72 grams. Just quickly check if it asks for any particular decimal places. Nope, so 41.72. Question 5 says, this question is about the electrolysis of aqueous solutions. Hydrogen gas and chlorine gas are produced when sodium chloride solution is electrolyzed. Hydrogen ions, H+, are attracted to the negative electrode. The half equation for the reaction at the negative electrode is, and it gives us the equation there. What type of reaction happens at the negative electrode? Give the reason for your answer. Type of reaction, reason. Right, let's have a look. So what is actually occurring? Well, you've got H+ and they're gaining electrons. Their H+ plus 2 electrons gives us a hydrogen molecule. What do we call that when something gains electrons? Well, I remember the term oil rig. Oxidation is the loss of electrons. Reduction is gain. So we're gaining electrons, so this is called reduction. How do I know? Because it's gaining electrons. Now we have to do a half equation. I can tell that straight by looking at that. Chloride ions are attracted to the positive electrode. Complete the half equation for the production of chlorine gas. Well, the first thing I'm filling in is chlorine gas at the end. I know I'm going to make it. It's just told me there, production of chlorine gas. So I know one of them will be CO2. I know I've got 2 chlorines on the right. Okay, I've got 2 Cl. So I need 2 chloride ions on the left. That'll balance my chlorines out. Now, each one of these started off negative and now it's gone to neutral. So what's happened? It's lost an electron. Each one has lost an electron. So plus 2E minus. This chlorine and the other one lose an electron to form chlorine gas. So each chloride ion loses an electron, and that's what we write there. We write the electron. Okay. Another long one now, 4 marks. Hydrogen gas and oxygen gas are produced when sodium sulfate solution is electrolyzed. Explain how oxygen gas is produced in the electrolysis of sodium sulfate solution. Okay, how do we get oxygen gas? And it's not, you can't just say, oh, because there's no halide present, we get oxygen. It's 4 marks. We need to be thinking, well, we've got to do a bit more than just one statement. So this is how oxygen is produced. Because this is in aqueous, we know that the water, and I'll put this into a sentence in a second, will break down into its component ions, which is OH minus and H plus. Okay? If you know that, we've got our first mark. Because it's in water or because it's in solution, OH minus ions are present. The water breaks down to produce OH minus ions. Those ions are negative, so they're attracted to positive electrodes. And when they get to the positive electrode, they lose their negative charge. Now, going back, what would we call that when you lose a negative charge? We call it oxidation. Oxidation is loss. There you go. And that's exactly what happens. They are oxidized and produce oxygen. Next question. So question 6, metal oxides are produced when metals are heated in air. A student investigated the change in mass when 0.12 grams of magnesium was heated in air. A student measured the mass of magnesium oxide produced. 0.12 grams of magnesium reacted to produce 0.2 grams of magnesium oxide. Calculate the number of moles of oxygen that reacted. Okay, the moles equation, moles equals mass divided by mR or AR, depends on whether you're working with molecular mass or just the mass of an atom in general. So first of all, to calculate moles, we need a mass. So what's the mass of oxygen? Well, we know that this is our mass of magnesium, and we know that this is the mass of our magnesium oxide. So if I take my magnesium away from my magnesium oxide, the remainder will be our oxygen's mass. That's what I'm going to do. So I'm going to do 0.20 minus 0.12. And I get a mass of oxygen of 0.08. Now I need to find the MR. Well, we call it the AR actually of oxygen. And oxygen is O2. Each oxygen is 16, so that's 32 for the MR of oxygen. And the final calculation is that divided by 32, which is 2.5 times 10 to the minus 3. There you go. Pretty straightforward if you can find the mass, otherwise it can be a bit tricky. Just remember that you're given the ARs, but you need to multiply them by 2 to get the molecular mass for that one. That's the only other thing I can see in there that's quite tricky. 6.2 and 6.3. So it says here that the student repeats the experiment without a lid on the crucible. Suggests why the mass of magnesium oxide produced would be different without a lid on the crucible. Well, if you leave the lid off, all that magnesium oxide will escape into the atmosphere, and therefore your mass will go down because it's not staying in the container. So mass will decrease. As products escaped. The next one says copper reacts with oxygen to produce copper oxide. 63.5 grams of copper produces 79.5 grams of copper oxide. Calculate the mass of copper oxide produced when 0.5 grams of copper reacts with oxygen. Give your answer to 3 significant figures. Right, well, what I want to see now is if I take 63.5 grams of copper, how much has it increased by? What's the ratio between my copper and my copper oxide? So that's what I'm going to do. I'm going to do 79.5 divided by 63.5. Okay, so now I know that it's changed by 1.25. I know that if I just lower my amount to 0.5 grams instead of the original 63.5, that increase will still be the same. I'm still going to go up times 1.25. I'm going to increase by that much. So I'm going to take 0.5 and I'm going to times it by, or multiply it by 1.25. And instead I make 0.625 grams. Okay, to compare the two, I've just looked at how much it's been upscaled by, so how much has it increased by, and then I've used that value and increased my 0.5 by the same amount. This one here says iron reacts with oxygen to produce iron oxide of iron, or an oxide of iron. 0.015 moles of iron reacts with 0.010 moles of oxygen gas. Determine the formula of iron oxide produced and balanced symbol equation for the reaction. Right, very similar to the previous one actually in terms of what we do in terms of the calculation. I want to know what the link is between these moles and these moles. We call that a ratio. So I'm going to do 0.015 divided by 0.010 because I want to see what ratio they have between them. Then I'll know how many ions I have in the formula and how many oxygens I have. So that's a 3:2 ratio. On your calculator it will look like this, 3/2, and I know it's a 3:2 ratio. So my formula of iron oxide is 3 lots of iron to 2 lots of oxygen. So I'm going to just show you that 1 second. So Fe, so there'll be 3 lots of iron and there'll be 2 lots of oxygen. So I have to put this into a formula now. So it's going to be Fe3O. I have 2 times 2 oxygens, so 4. Fe3O4. That's the tricky part, really tricky, because most people will be tempted to do Fe3O2, and that won't work because remember it's 2 oxygen molecules, which is 4 overall, not 2 atoms of oxygen. Very tricky. If I show you the balanced symbol equation, it might make it easy for you. So this shows me I've got a 3:2 ratio. So I start off with 3 Fe and I react it with 2 O2. Okay, that's your starter, that's your 3:2 ratio. And that will make Fe3O4. 3 ions and 2 times 2, which is 4 oxygens. All right. I think we're near the end now. It says methane, ethane, propane and butane all react with oxygen to produce carbon dioxide and water. Suggest why a mixture of methane and oxygen does not react at room temperature. Answer in terms of particles. Well, everything collides. Particles are colliding all the time, but they don't collide with sufficient energy to start a reaction. They don't collide with enough activation energy, and that's the answer here. So if they don't collide with enough energy, no reaction will happen. Okay. 7.2. Table 3 shows the energy released when methane, ethane, propane react with oxygen to produce carbon dioxide and water. Predict the energy released when butane, C4H10, reacts with oxygen to produce carbon dioxide and water. Right, I'm going to look at how much it's increased by each time. And then I'll know what the next increase is. Okay, I know that the molecule after will be C4H10, so I'll know that whatever that increase is, we'll have our energy released. So for that, I'll do 1640 minus 1160. So 1640 minus 1160, that gets us 480. And I'm going to add 480 to this, and I'll find out what my missing bit is. So the energy release will be 2120. An increase of 480 each time will take me to my new energy, which is 2120. Right, this one says propane reacts with oxygen to produce carbon dioxide and water. The displayed formula equation for the reaction is, and it shows us there, the reaction is exothermic. In the reaction, the energy released when forming new bonds is 1640 kilojoules per mole, greater than the energy needed when breaking bonds, and it shows us the bond energies in table 4. Calculate C bond C, or calculate the C bond energy X. Right, this can be really tricky. So what we're going to do is we're going to copy any bond number or any energies, we're going to copy them onto the bond, okay? So let's do the first bit. So I'm going to split this down to left and right, and you'll see why later. I want to know all of the energy on the left, all of the energy on the right. So we've got 410, and that's for each carbon-hydrogen bond. And I like to write it on each one so I know I don't miss any bonds by mistake. Because what usually happens is students know what to do, but they're in the exam conditions, they rush and they miss maybe one of these. Now luckily we were trying to work them out, but you don't want to miss any of them. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 4, 10. So we're going to do 8 times 410 plus 2x, because we don't know what that is, that's what we're trying to work out, plus 5 lots of that, which is 500. Then we're going to move on to the right side now. And we've got this O double bond C here, which is 740. And we've got 740 here. And we've got 3 lots of those molecules. So 3 times 2, that's 6 in total. And we're going to add that to HOOH bonds, which are 460. And we've got 4 times 2, so 8 in total. Now, here's another point, this will get missed. So it says that the energy is, the reaction is exothermic, and it releases 1640 kilojoules per mole of energy. So that's given out at the end, that's lost, 1640. Now, the reason it's minus is because it's exothermic. And any energy change that's exothermic has a negative value. So that's how you know, and that goes at the end. If it was endothermic, it'd be positive and we'd add it. But it tells us that here, and if you miss that, then you're obviously not going to get the right value. So now we need to sum up the left and the right and find the difference. So let's have a quick look. So the left side, we're going to have 2x, and we're going to have 8 times 410, and we're going to add that to 5 times 500, so we get 5780, and on the right hand side we have 6 times 740, and we're going to add that to 8 times 460, and then we're not going to forget to remove the 1640 from that side. And for that we get 6480. We want the 2x on its own, so I'm going to move this 5780 to the other side. When I do that, it becomes a negative or a minus. So 6480 minus 5780. Scroll down a little bit. So 2x will give us 700. But of course we don't want 2x, we just want x. So to find x, we're going to divide 700 by 2. and we get 350. Each one of these is 350. It's given us our units, but we'll write it on for completion, kilojoules per mole. Okay, hopefully you can see how we did that. That is a tricky question. I don't know if they'll do something like that this year. That seems very, very tricky. But again, it is the last question on the paper, and therefore it's probably the hardest question on the paper, or certainly the highest level anyway. If you need any support with anything that's been in this video, please pop it in the comments and I'll do my best to explain it a bit better, maybe in more detail. Likewise, if you need any more questions, just keep them coming. Let me know what paper you want to do, or any parts of this paper you found tricky. We can focus on them next. But until next time, see you soon.